This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So now I want to talk to you about, let us suppose for the minute, and we're going to have several of these, actually 4 of them, of these important functions that are known as canonical equations of state. So supposing you knew, and I'm going to tell you why it's a canonical equation of state, and that's going to be very important when we talk about the enthalpy, for example. So here, let's suppose the internal energy. Supposing you knew it to be a function of the entropy and the volume. So we're going to say that E is S of V, in which case I can write down mathematically that the change in E is dE ds at constant volume plus d, wait a minute, that's not correct. Where's the eraser? Ah, sorry. Thank you. Delta S plus dE dV at fixed S delta V. So now you can see from this equation here that dE is equal to T ds minus P dV. So if you had this expression, you could, if you had this function, you could take these derivatives and you would deduce that T is equal to dE ds at fixed volume, and that minus P, or P, is equal to minus dE dV at fixed S. So you can see that I could, if I knew E of S and V, I could find T and I could find P at any particular S and V, and correspondingly I could, so that's what I've just written here, and right. So if we knew E in S and V, we would know T and P, and therefore we could construct any other function that we liked. For example, we could construct clearly the internal energy as a function of the temperature and the pressure, and the volume, sorry. And that equation specifically, E of T and V, is called the caloric equation of state. And I could also create from that P as a function of V and T, which would be P as a function of V and T is called the thermal equation of state. So E, because E of S and V can find all the thermodynamic variables, from which you can construct these other equations of state, it's called a canonical equation of state. And it completely describes a simple system, namely P of V and T, E of V and T, and S of V and T. I could calculate those things. So when you find tables, all of this must have been true. Now, something that we're going to use a lot is the enthalpy, and I'll explain to you why, but let's introduce it first. The internal energy, the enthalpy, I'm sorry, is another composite function, like the one that I've just described, the internal energy, E of S and V. Suppose we could construct H of S and P. Now that H of S&P will be familiar to you because it's often charted as a Mollier diagram. And we could also construct G of T and P, and G is called Gibbs function, or the Gibbs free energy, and it is H minus Ts. That's another canonical function of state. All of these things are equivalent in a way. You can get everything from them. And there's another one called F, which is E minus Ts, and that's sometimes called the free energy. Now, why? So let's look at dH. H is equal to E plus PV, right? So dH is equal to dE plus P dV plus V dP. But dE plus P dV is TdS. All right? So I'm talking about this equation here, E plus PV. So dH is dE plus P dV plus V dP. That's obvious to you, right? But dE plus P dV from the first law and from what we've developed is the entropy as a variable of state, So that dE plus P dV is dQ, which is TdS. And so then we've got that plus V dP. So now, by the same trick as what I did here, I can arbitrarily take this function, H of S and P, and do the following. And you'll see then immediately why it's an canonical equation of state. Because so H of S and P would be, or dH is equal to dH ds at fixed pressure, delta S, plus dH dP at fixed entropy, delta P. But that's exactly of this form here, so I can identify T and V, and what I've done for you there is show you that T is therefore dH ds here, so that's the TdS, and dH dP is the V dP, and so since I can now find T and V, I can construct all of the other variables of state, or equations of state. Caloric equation of state, thermal equation of state, I can get them all. So I get them all from one function, H of S and P. And that is called a canonical equation of state. The same is true for the Gibbs function. Gibbs function is defined to be H minus Ts. Well, so H minus Th will be, dG will be dH minus dTs minus SDT, and that will be TdS. Well, I've written it down here. It's dG will be TdS. So this is the dH part. dH part, yes, is TdS plus VdP. Yes, here. And then I have to subtract minus TdS minus SDT. And you can see that the TdS cancels and I get a VdP minus SdT. So, so I can get the V and S, and so H of S and P is a canonical equation of state, and it's often charted, and you will have seen it, I hope, before, as a Mollier diagram. And why is that of interest to us particularly? It's because in flow processes, typically, they are sometimes idealized as isentropic for part of the process. No, the entropy remains constant, and they're isoenthalpic. They don't change the enthalpy for reasons which we will make plain. All right, now this is a bit theoretical, but I just want to mention it because you will have seen it before, I hope. And that's Clerk Maxwell from electromagnetic theory worked on thermodynamics, and his relations, four relations between partial derivatives are very well known. So I just wanted to mention them. As I said, if you had a canonical equation of state, E of S and V, from which you can find T and P, then, and I showed you how we would do that. So I found T and P from this equation. And now what you can notice is that if I take the partial derivative of T with respect to V, I'll get that that's equal to the partial derivatives of d2E ds dV. And so that's dt dV at constant entropy would be that, or this rather, from that. And if I took the partial derivative of this with respect to the entropy, now at fixed volume, then I'd also get this term, and so this must be equal to that. And that is one of the four of Maxwell's equations. And that one comes from the canonical equation of state, E of S and V. If I do exactly the same thing, and I've done it for you here, for H of S and P, I get dt dP at fixed S is dV ds at fixed P, and that's because d2H dP ds is the same for both of those. And I can do the same thing now for G, and I get the third of Maxwell's equations. dV dt at fixed pressure is minus ds dP at fixed temperature. I mean, these are seemingly bizarre connections, but they're buried in this canonical equation of state. They must be satisfied. And the free energy, F of T and V, will give it the fourth of Maxwell's relations. Now I want to talk about something that's going to become very important to us, and that's the ratio of the specific heats. Why is that curious and important? So I have to say something about it. So now, this is intensely irritating here. I don't know why to. Right.
Yeah, I just want the top left. If you just click the X here.
There's no X there.
Well, there's a red dot, right? If you just click that, yep, you'll kill it. There you go.
Thank you. Right. So now, what is the specific heat? There are two ways to define the specific heat. There's more than two, but there are two that are commonly used. One of them is that if I add an amount of heat, dq, and I change the temperature, dt, and I do all of that at fixed volume, then I get what is called I get what is called the specific heat at constant volume, CV. All right, so now you can see from the first law, dq is dE plus pdV. If I hold the volume fixed, then I don't have this term here. And so dq will be the change in internal energy. It's the partial derivative of the internal energy, and it's of unit mass. So that's why I've used the lowercase. So it's unit mass. CV is the amount of heat I need to change unit mass by a temperature delta T. And I've got to do it at constant volume. So that is what is, by definition, CV. And CP is the same thing, only I'm not going to do it at constant volume. I'm going to do it at constant pressure. So if I do it at constant pressure, you can see from dq, remember that H by definition, the enthalpy by definition, is E plus PV. So dH is dE plus pdV plus VdP, right? So in this equation here, I can write the dE is dH minus pdV, so that'll subtract from that, and then I'll minus VdP. So that's from the first law and the definition of the enthalpy. So instead of, so CV is obviously at fixed volume, dE dt, and CP is at fixed pressure, so that would be 0, and the dQ would be dH, the change in the enthalpy, dH dt at fixed pressure. All right, now I can do some more playing around here and show you why the ratio of the specific heats is a quantity of interest. So you can also see that dE dt, if dE is TdS minus pdV, and I'm going to make the volume constant, so I don't have any pdV, then dE dt at fixed volume will be simply T, I'm dividing this by delta T. Wait a minute, I should do it on the blackboard. So CV is dE dt, and CV is from here. dE dt would be at fixed volume, this is not there, it would be T ds dt at fixed volume. So another way to work out CV would be to have some equation for the entropy as a function of T and V, which I could get from my canonical equation of state, E of S and V, for example. And I could get all of this. And so this CV would be ds dt at fixed volume. But CP is dH dt at fixed pressure. So dH dt divided by delta T at fixed pressure, this is 0. That will be T ds dt at fixed pressure. And so gamma, the ratio of these specific heats, CP over CV, will be dH dt divided by dE dt at fixed volume. This is at fixed pressure, but this is also equal to the ratio here of ds dt at fixed pressure divided by ds dt at fixed volume. So that's rather simple. And now we could go one step further and work it out. So, if we had an equation, and S is an equation of state, if S is a function of V and T, and P is a function of V and T, then this is, all right. This statement here is mathematics. That's just for a function of two variables. That's a statement of mathematics. So now I can work this out. Let me take ds and divide it by delta t and do this at fixed pressure. Then that'll be this term, dv dt at fixed pressure, plus ds dt, and I'm dividing by this delta t over here. I'm dividing, I have ds dt at fixed volume. So that gamma, which is ds dt at fixed pressure, becomes this, ds dt at fixed pressure becomes this expression here. So it's ds dt at fixed temperature, dv dt at fixed pressure, plus ds dt at fixed volume, divided by ds dt at fixed volume. So this will cancel with that, and I'll be left with this divided by that. 1 plus that. Now that happens to be greater than 1. And for almost any substance. Now I want to be a bit more specific, because we're going to approximate in the fluid mechanics of compressible flows. We're going to approximate the fluid typically as a perfect gas. But there will be many occasions potentially where that's not true. We might be looking at water, for example, or steam. Steam might be approximated under some conditions as a perfect gas, but not under others, because it condenses. So we want to be able to be very clear about when we're talking about perfect gases, when we're talking about some other arbitrary fluid. If you were looking for a cutting jet made out of very high velocity water, and people cut stone with water after all, you'll need to know, in order to design the nozzle for the supersonic stream of water, you'll need to know the equation of state. So you'll have to go to tables. All right, so now let me remind you of what I did yesterday. What is a perfect gas? A perfect gas is one for which P is equal to nKT. Or alternatively, if you multiply by m, the mass of each molecule, particle, and divide by m, then that's the same thing as mn k over mt. And k is the Boltzmann constant, and I gave its value to you yesterday. And k over m is the gas constant R. And mn is, of course, the n is the number of particles per unit volume, multiplied by the mass of each particle. It must be the mass per unit volume, and that's the density by definition. So there's rho. All right, and so I've written here that that R, the gas constant, is k over m. And if I multiply both of them by Avogadro's number, which is the number of particles in the molecular weight, then it's k times n is what's called R mole, and m times the number of particles is the molecular weight. But as I've reminded you, the molecular weight that you know typically is in grams. But we need, in consistent SI units, we're going to need it in kilograms, of course. So you're going to have to divide it by 1,000. All right. Now, a perfect gas is now, oh, good God. I'm sorry. You'd have thought I didn't know what I was doing. We've done all of that. Right. So now, a perfect gas is one for which P is rho RT, or P is NKT, choose whichever, but also a perfect gas is one for which the internal energy is only a function of temperature. And behind that idea is the idea that the particles or the molecules that we're talking about are non-interacting mass points. They don't interact. In other words, they're mass points. They have no physical dimension. They don't have a diameter. Well, of course, that's not true. And we're going to work it out. But one of the great experiments in science, in a way, in thermodynamics, was done by Joule. And he did a great experiment with hydrogen and established that the internal energy from the first law of thermodynamics was only a function of temperature. So how did he do it? So I've sketched it here. What did Joule do? And you can't imagine how radical this was at the time. You take it all for granted, but it was radical at the time. So this was what became known as the Joule effect. And so he's going to prove that dE dP at fixed temperature is 0. It doesn't depend on pressure. E is only a function of temperature. So what did he do? He started here with a vessel full of hydrogen, and over here he had a vessel that was vacuum. And here he had a valve between the two. And he opened the valve. And of course, he did it in a way where he tried to make all the walls adiabatic. So he did it with flasks and so on, so that there was no heat supplied. And self-evidently, there was no work done external to this system. There was no work done on the system. So Q was equal to 0, and W was equal to 0. And so from the first law of thermodynamics, it had to mean that there was no change in the internal energy. So that comes from the first law. So he assumed the first law. And then he said, but if E is a function of T and P, two other thermodynamic variables, then I can write down that dE is dE dt at fixed pressure, delta T, plus dE dP at fixed temperature, delta P. What was the change in pressure? Well, it was enormous, enormous. You started here in a small volume and you expanded this thing out into a bigger volume. So the pressure went down. There was an enormous change in dP. But there's no change in dE. So he said, if delta T was 0, so he could measure the temperature here, and then he could measure the temperature here after it reached a new equilibrium point. He could measure those temperatures. If those temperatures were 0, then this term would be 0. This term can only be 0, since delta P is not 0. This term can only be 0 if this term is 0. So of course, he knew that he had to have that the internal energy change was 0 from the first law He measured the temperature here and he measured the temperature there, and there was no change in the temperature. So he measured it, you know, in those days he measured it with probably a mercury thermometer. I don't know whether he had anything else to do it more accurately. And so he deduced that this term must be zero. This term zero. So E, he concluded, was only a function of temperature. So, yes?
How can we relate this to what we said earlier, that state depends on two variables?
Because we're now talking about a perfect gas. What we were talking about earlier was an arbitrary fluid. Arbitrary. Water, anything you like. An arbitrary, homogeneous fluid. And I began the whole thing by talking about the equation of state. What do I mean by a state? And it had to be in equilibrium. And in that case, it's found experimentally that if I set the same pressure and the same volume, I always get the same temperature. Right? Arbitrary fluid. Yes?
I've got a question. You said the left side was pressurized and the right side was vacuum. And obviously the pressurized side, the pressure would decrease when you open the valve. But wouldn't you take the pressure as like an average of both systems?
Yes, but you're taking the system at T equals naught before you open the valve, and then you open the valve and you've got a big volume now. And the pressure has obviously gone down. So you've got an initial state and a final state. And those states are states now. There are no currents. You wait long enough so that there's any heat going to and fro, whatever happened. If it got hot here and cold here, then you wait long enough until you reach uniform temperature. And you therefore have a state. Right?
Do we have an increase in volume?
We obviously have an increase in volume. And we have a change in the pressure, delta P. But we know from the first law that there should have been no change in internal energy for the whole system. But it could have been, you could have had this term and this term. But you didn't have this term. Why? Because he measured it. Yeah?
When we talk about like delta Q equals 0, delta W equals 0, which system are we talking about?
The two volumes. The two volumes.
Then if the gas is expanding, how do we make sure it's not doing work to the outside?
Because it's in two volumes that don't change. You've got one with vacuum in it, and
so
one.
it's like sealed on both sides.
They're sealed volumes,
Okay.
and you have a valve in between, and you open the valve. All right? So the whole system doesn't do any work. And you've set it up so that it doesn't actually take any heat. One heat will go from one side to the other, but you wait long enough. Because, you know, one side is down here, it'll get hot initially, and this other side, which is expanding, will get cold initially. But you wait long enough, and then you... Beg your pardon?
I mean, it will become like a homogeneous.
It becomes homogeneous. Yes. That's the, I mean, it's remarkable. It's remarkable. So this is, no wonder we name energy after Mr. Joule. Experiment, he did the experiment in hydrogen and deduced that E was a function only of temperature. All right. So now we're going to go further. We're going to remind ourselves that by definition, CV what happened here? Does it switch itself off? Or is the battery gone flat?
Okay, I think we have a dead battery. Sorry.
Okay, but I can explain what I'm going to say. Look, here. CV is the EDT at fixed volume, but we just determined that E is only a function of temperature. So it's the ordinary derivative. It's not a partial derivative anymore. It's dE dt, right? And that Cp is dH dt at fixed pressure. Well, now H is E plus P over rho, so that E is only a function of temperature. P over rho is RT for a perfect gas. For a perfect gas. Beg your pardon? Miraculous, thank you. So we can say immediately that for a perfect gas, H is only a function of temperature. And so this dH dt at fixed pressure simply becomes dH dt. H is only a function of temperature. Now that's magic. So, for an ideal gas, E, H, CV, and Cp are functions only of the temperature. Why? Because this ideal gas has P is rho RT, and E is a function only of temperature. That's the Joule effect. So now, we can go on. Now, we make a bit of a leap. We say, what if we had an ideal gas with constant specific heats? So that's a postulate. They don't have constant specific heats, but supposing they did. So in this case, E would be CVT, and especially if you said, I'm going to integrate from absolute zero, so there's no T naught. E would be then CVT, and if I integrated from absolute zero in temperature, H would be CPT. And so I'd get a very simple relationship between E and H, remembering that H is E plus P over rho, or that H minus E, and H minus E is Cp minus CVT. So H minus E is clearly P over rho, and P over rho is RT. So let's get to the next line. So H is CPT, E is CVT. So if I put this in here, I'll have the T's will cancel. I'll have H is, so H minus E is Cp minus Cv, both of them times T, and this is RT. The T's will cancel. And so I deduce the remarkable result that we're going to use quite frequently, is that Cp minus Cv is R, but Cp is gamma times Cv. So I can pull, so I have a gamma minus 1 here times Cv. I pull the Cv out and divide by gamma minus 1, and I get an expression for Cv, which is R over gamma minus 1. And because Cp is gamma times Cv by definition, Cp is gamma R over gamma minus 1. So we're going to use that quite frequently. Quite frequently. You're going to have to know it. All right. So now let's go on a bit. Now, I'm not going to do it for you, but if you were to study kinetic theory, and some of you may have done, then you would know that gamma is related to the number of degrees of freedom. So for a monatomic gas, it's 5/3, and for a diatomic gas, it's 7/5. I hope you know that. How many of you don't? Good. You don't know it. Okay. Well, you need to know it. You need to know that kinetic theory gives you this result, where alpha is the number of degrees of freedom. So how many degrees of freedom has a monatomic gas like argon got? How many degrees of freedom? 5, 3, 2, 1? How many? Anybody know? Nobody knows? Good God. A monatomic gas has 3 degrees of freedom. It can go in this direction, or this direction. Now, what about a diatomic gas? How many degrees of freedom does it have? Anybody know? A diatomic gas. Who said 5? You're right. Why did you say 5? There's, in addition to going up, across, or down, or back, 3 spatial directions, it can rotate, but it can rotate with significant energy, only not about the axis between the 2 atoms. We're going to ignore that. We're going to rotate this way and this way. So that's 5 degrees of freedom. And a polyatomic gas has all degrees of freedom for rotation and translation, so it has 6. So gamma for a polyatomic gas will be 8/6. A diatomic gas is 5/3. 7/5, and a monatomic gas is 5/3. So now I'm going to work out something for you because, yeah?
What about CO2? Because the angle is 180 degrees, but it has 3.
Yes. I should think CO2 is polyotropic, but I don't know.
But it has only 2 degrees of freedom about rotation.
Does it?
Because, it is 180 degrees, so...
But is there not some inertia for the other?
So still, it is...
CO2 has got 3 atoms.
The carbon is in the middle, and the oxygen, 2 oxygens on both sides.
Yeah. Oh, okay. On both sides? Yeah, maybe it's 5. Maybe it's 5. I don't know, to be honest. I don't know. And, kinetic theory is an approximate theory. You're assuming that there's insignificant energy in the other rotational axis. And that's probably true for CO2 on reflection. Probably. All right, now I want to do something that we're going to use a lot. You already know the answer, but you don't know how to get there, probably. Or you have got there before, but you've forgotten how to get there. So supposing I wanted to know the entropy of this ideal gas with constant specific heats. So I should be able to work it out, right? So I write down the first law. TdS is dE plus PdV, or that because now S is a variable of state, I can work it out. ds is CV. Instead of dE, I'm writing CV dt, and then dividing by t. So ds is CV dt. CV dt is dE. And So I've got a P dV here, and I'm going to divide that by a T, and this dV is d of 1 upon rho. And so that'll be a minus. It's not a plus, it's a minus. I've written it correctly. There's something... Yes. So this dV is d of 1 upon rho, which is minus 1 upon rho squared d rho, right? And so I've got the rho squared, and I've got the t, and the minus p, and I've got a d rho here. So I have this expression. And P is rho RT, so this is minus R. So ds is Cv dt minus R d rho over rho. But now, I hope you know that if I have an expression like P is rho RT, and I want to differentiate it, you can be there until hell freezes over playing around with that. But I'll tell you the trick. Why don't you take logarithms of both sides? So you have log of P is equal to the log of rho, log plus the log of R plus the log of T. Now differentiate that. And if you differentiate the logarithm, you'll have dP over P is equal to d rho over rho. Differentiate that, you'll get 0 plus dt over t. That's a simple way to get there. That's the, if you've done it before, that saves you a lot of time. All right, so what I've done is change dt over t by dp over p minus d rho over rho. So here it is here. Here it is here. And I've got minus r d rho over rho. So so if I change that r to Cp minus Cv, then I'll cancel this d rho over rho, and I'll have, so I get Cv dp over rho minus Cp d rho over rho from here. And that means now if I divide by Cp, sorry, if I divide by Cv, it would make more sense. So now I take this this ds and divide it by the Cv, and I get ds over Cv is dp over p minus gamma d rho over rho. Cp over Cv is gamma. So that's d rho over rho. So I can now integrate this very easily. So I get S minus S naught over Cv is the logarithm of P minus the logarithm of P naught, which is the log of P over P naught, minus gamma log of rho over rho naught, or this P and minus gamma logarithm, I can change this by putting the gamma inside here. And so this is the logarithm of rho to the gamma over rho naught to the gamma. And then I have the logarithm of P minus the logarithm of rho to the gamma, which is the logarithm of P over rho to the gamma minus the logarithm of P naught over rho to the gamma. Very simple. So we've deduced that if so we can regard this as some sort of a constant, and this as a constant. And it follows that P over rho to the gamma is a constant, because if I took the logarithm of this, I'd have the logarithm of that plus the logarithm of that, which is a constant, plus the logarithm of this would be S over CV. So this equation of state deduces for us that P over rho to the gamma is some constant S e to the S over CV, or this equation of here. So this is the equation of state relating for a perfect gas of constant specific heats. It relates the pressure and the density to the entropy, or the pressure and the volume to the entropy. Now, I've got to watch the time here. I'm nearly finished for today. So you can see immediately that for a perfect gas, if the entropy is constant, P on rho to the gamma is a constant. So you see, you saw what I did before when I had that Carnot cycle, and I said it's adiabatic on the side, and we'll make it isentropic because we'll make it reversible. So it goes through a sequence of equilibrium states. And so I wrote PV to the gamma was a constant. Well, V is 1 upon rho. So that's P on rho to the gamma here. So that's where that came from. It's do all of you know that? Yes? Or do I assume no? Tell me. You have to tell me. Do you recognize that? No. Good God. Okay. Well, that's what I've done has been important. It's important. These things you will need to know, because we're going to use them in spades. So why? Well, let me close with this. What is the application of thermodynamics to a moving fluid? Here's the heart of the matter. Firstly, the quantities that describe the fluid are either scalar or vector fields. Now, what is a scalar field? Rho is a function of x and t, where x is the position. So the field is this room, and there's some point here which is x, y, and z, and there's some point at some time. Before I open the door, it'll be uniform in here. No, not quite, because you're all breathing. But I'll open the door. If you all died, it'd be a uniform state. Okay, so this is the density is the mass per unit volume. So I'm talking about very small volumes and very small amounts of mass, so I can define a density, dm over dv. The density is the mass per unit volume at the specific point everywhere in this room, x and at the time t. So that is a scalar field. What is a vector field? Well, a vector field is simply that at every one of these points, there is not only a scalar, there is a vector. And a vector is an object that looks like a step in space. It has a direction and it has a magnitude. So it's a vector. So you could, it clearly has three components, because you could make the step arbitrarily in this direction, which is a little bit in this one, and a little bit in this one, and a little bit in the other one. Three directions. So that's why I will use as a vector quantity an underscore. That'll mean that it's a vector, like I've done here. So what we are doing is we're disregarding the corpuscular, namely the fact that the fluid in this room is made up of a whole lot of molecules. How many are there? Well, I'm going to show you how many there are. It's a big number. But we're going to disregard the corpuscular nature of the fluid as long as the characteristic length of the change of a macroscopic quantity, for example, rho, is much larger than the molecular spacing. So if the molecule